Okay, we're recording, and let me, there's like a way to hide this. Hide video. Hide. There we go, because then it doesn't show up in the record. Nice. Okay. Hello, all of you survivors of midterms. Welcome to the Data Science Club for March 9th, the before break. So everyone's very burnt out, and I'm sure we're all looking forward to a week off. Let's see. So just some updates, still looking for e-board, but I'm pretty sure we're like talking to an audience of people that are all graduating. So, it might just be Sujan's club next semester because we might not have anyone to actually take over. Again, DataFest planning, which we had a meeting for Upstat last night. So DataFest isn't here and they're already playing the next conference. But we'll talk about Upstat after DataFest, just like how we wait to talk about DataFest after BrickHack, because they're just like things in a row. But yeah, so we're slowly getting speakers. Like I think we have like 5 speakers so far. So I think some of you will probably talk as well. Maybe we'll be up to 7. But yeah, we'll see what happens. We might have to bug faculty if not enough students sign up to speak. But yeah, it should be good. We got flyers out. So you might have seen our flyer. I kind of pinned these up all around Golisano trying to get more traction. But yeah. Obviously come from an e-board, but again, we addressed this problem. So tentative schedule, we were supposed to have a guest speaker today, but the guest speaker had a travel thing come up, so they had to bail on us like 3 days ago. So we're just switching our guest speaker with one of our special topics, our first special topic, time series analysis. So I hope that is interesting to y'all as well, and you're not disappointed by the lack of neuroevolution in this talk. So yeah, we're gonna start on time series analysis. So you might be asking yourself, what is a time series? The name is a little bit misleading because 99% of the time, time series is over time, but it doesn't necessarily have to be time. When you say time series, you're really just referring to any sort of sequential data, really. So this is a cool little cartoon where temperature over time would be a classic time series, but then they have one where it's like a tree and it's like the ring width and the number of rings. So like you're looking at the age of a tree as you go out with like the radius. And there's one with a signal and it's like magnitude over frequency. So like as you change the frequency, how does the magnitude of your signal change? And all these things can be considered time series. You can use the same modeling and approach to study them, but they're not the traditional like over time data. So there are different types of time series, and there's an entire vocabulary to describe these time series. So one is simply trend, or you also see this referred to as non-stationary, which is basically, line goes up. There is no trend or stationary, where we see here, this one does not appear to have any obvious trends over time. And it can also be called stationary because like it's referring to the mean is stationary. Like if you're taking a mean of this data, it would go flat across it. It wouldn't go up like the trend one. There's also seasonal data. Seasonal data is data that has very, expected repeats in it. Like if we looked at the temperature over the year or years, we would see seasonal data because, every month, barring global warming, tends to have the same temperature every year. And then there is kind of the catch-all term, I think, because like cyclic data is when the data has fluctuation in it, but it's not regular and seasonal. It's just kind of random like noise in it. And we'll get into this. Also, you can obviously have types of time series. So you can have multiple types as well. So like you can have a seasonal with trend. So this is simply, it's seasonal data, but the mean of it is also trending up. And the same thing with, you can have like cyclic data with a trend. So it's pretty random and cyclic, but it also has a mean that trends up. And usually how we analyze these types of times series is you do time series decomposition. So you can take out the different components of a time series, especially if it has very obvious multiple behavior. So here we see a time series that is both seasonal and has a trend. And you can actually break it up into the seasonal component, break it up into the trend component, and even break out the random noise. And then when you go to analyze or model this time series, you just use a composition of all these behaviors and kind of treat it as the bulk. So like you could fit the seasonal and you could fit the trend and then kind of combine those models together, which again, we'll get into. So what is the power of time series data? Because we see how something behaves over time. And what we want to do is we want to understand this data over the time period we have, and then use that to forecast in the future. So we're using our previous data to try and predict the future. And how are we going to do that? There are a whole host of time series models. So there's like trend models, seasonal models, exponential smoothing, and something called ARIMA, which is very common. I see ARIMA everywhere. And technically we can use like RNNs and transformers, a lot of fancy deep learning, but we've already covered RNNs. And honestly, in the time series class I took and inside time series literature, people try to stay away from these really big, deep kind of black box models, especially if there are simpler and just effective models, because you'll save on computational time, you have more explainability. So we're kind of going to go over all of the non-deep learning. So there's some light machine learning ones, but not very sophisticated, just like your regression models that are basically optimization. But we've already seen RNNs. We can use them, but let's go over the things used in time series analysis that aren't neural network based. So first is the most basic kind. I think we've all encountered these before. They like just the line fitting models, like the most basic type. Like you get your linear regression, you're just fitting a line. You get your exponential regression, you're fitting an exponential function, and you get your polynomial regression. Basically, you give it the equation, and then you find the weights through a loss function. And similarly, with seasonal models, you can use a trigonometric regression, which is another kind of trend model, but you're fitting a trig function to your seasonal data. We know a trig function has seasonal repeats, and you can match those up with your seasonal data and get a line that fits it fairly well. Then we get into something called dummy variable regression. This is where it gets a little bit more involved. So a dummy variable regression does this is like yearly data. So we have January through December. And what we do is if we know we're at January, we kind of set a weight for January, and we have weights for every month. These are the dummy variables because we're generating more variables in the model that don't exist. Because in the base model, you only have time, but we're saying we're splitting time up into months artificially. And every time we hit a month, we basically kind of turn that weight on, like we activate it like with a 1, and then all the rest of the months are 0. Kind of what it does is almost like linear regression, but you have, in this case, 12 different lines fitting, like, let's say these spikes correlate, like you have January here, then February, March, and then it spikes in, June. You can imagine it as you're fitting a line to every month and kind of switching on that month when you're at it. So you get this equation, which is a weight plus kind of like an activation function for every month. And as you hit each month, you activate that weight, and thus, fitting your seasonal data. And then we're going to get into exponential smoothing, which this is a pretty neat one. I've kind of made it more succinct. There are more sophisticated exponential smoothing models, but it's basically the reason it's called exponential smoothing because every next point you take is taking exponentially more points, because the idea behind this is you want to use every point before the point you have to predict its value. So like if you're on your 30th point, you want to use all 29 points before it to try and predict what that 30th point is. And how you do it is you basically if you're at point n, you take n minus 1 until you get to, all your points, and you add a discount factor, which is basically a weight of like how important this certain, point is to the current point you're trying to get. And it's usually, the nearest points to the point you have are going to be weighted heavier. And as you go down the line, they're going to, have smaller and smaller significance. So like here is a little example that I put as a exponential smoothing. So let's say I start with an initial weight of 0.5, and I am basically saying that every weight is going to be the square of the weight before it. So if we want like x of n or f of x of n, we're going to do 0.5 times f of x minus 1 plus 0.25 and keep having it as you go down the line. So, once you get all the way down the line, that point is going to matter very little because it happened, further back temporally. And then the closer points to the point you want are going to be heavier weighted. If you want to look into this, there are some really fancy discount factor schemes. You have like first and second order exponential smoothing where the weight of every sequential point that you're using is like very intelligently weighted off of the points you've already used. But I just made a very simple example so you can see how it works. Now we're going to get into the fancy stuff, which a lot of terminology we have to cover, but we're going to make it. So ARIMA stands for autoregressive integrated moving average. So I know like two of those words, maybe a third one, but I don't know what it means in this context. So I just broke down kind of each of these terms, and you put it together when you do the model anyway. So first term, we have autoregression, which autoregression is how much a time series regresses to itself, or basically how well do previous points in your time series predict the next value. And the way we measure autoregression is something with partial autocorrelation. It's kind of weird introducing partial autocorrelation before I introduce actual autocorrelation, but that's going to be later. And you can kind of think of it as a measure of how autoregressive a time series is. And we can look at a partial autocorrelation plot, or these might be autocorrelation plots. I might have messed up here. But they're going to look the same. But it's basically, if you have a time series, you're going to see how many lags or how many points before each point correlates with it. So if you have like, your nth point, how much does the n minus 1 correlate to it? If you have n minus 1 point, how much does n minus 2 correlate it with it? So this one, the points in this sequence are not very correlative at all. So you see the autocorrelation, it goes back lags or like points before. So obviously with 0 lags, the point correlates 100% with itself. But even going back 1 lag or the point before the point you have, there's like no correlation. This translucent box here is your significance value. So if it's below this, you can say it doesn't have significant autocorrelation or partial autocorrelation. So, I mean, over here, you can kind of get a point that, correlates, but this might be superfluous because it's so many lags back. But if you look at something like this data, there's very high autocorrelation, which means that if you have the points before the point you're at, they're going to correlate very well with the point you're at. Now, integrated trend, or this is what it means by integration or integrated. It basically says what is the degree of trend you have in your model. So you measure your degree of trend by differencing, which is basically subtracting each sequential point in a time series to find out how integrated the trend is. So here, if we take like n minus n minus 1, n minus 1 minus n minus 2, you kind of get this difference graph. And if you see here, there's a trend in this graph, but once you do the differencing, there isn't. So we would say it has a degree trend of 1, because you only need to take 1 difference before the trend goes away. Here's some seasonal data. So what we can do is called seasonal differencing. So instead of subtracting each sequential point, you subtract each seasonal point, which means like if you had monthly data, you'd subtract every January from every other January. And in this one, you actually, I think, need to take 2 differences, because you can take a difference here. This is the first difference, but you see a bit of a trend here. So you take a second difference, and then you see the mean is very flat. So we would say this has a like second degree trend inside of it. Finally, we have to go to moving average. So like moving average is smoothing out a time series by taking a rolling average, which is basically averaging within a window. So I have a little graphic here that shows an example of moving average. So each of these lines has a different rolling average window. So like this line has like a 50-day rolling average, which means there's a couple ways they can do rolling average, but I think they might have used midpoint rolling average, which is basically every point you take like 25 points before it and 25 points after it, and then you average that, and that's your new value for your line. And then they have 50, 100 day, and it's basically just your kind of smoothness factor. Oh yeah, these are the same graphs you saw before because I messed up and I didn't put partial autocorrelation, but we'll see that later. So autocorrelation is how much points in a time series correlate with each other. And there's some very particular mathematical difference how it's different than partial autocorrelation, but I have to look it up again. And autocorrelation can tell us the moving average window we should use because it tells you like how significant are the other points to predicting the point you have. So you can be like, okay, this one, well, the points we have aren't really, predictive of the next point. So our moving average window can be pretty small because if we average this data, we're going to lose a lot of the information, smoothing this out. But if you take this and you smooth it out, you're still going to keep the trend, and your averaging window can be fairly large, and you'll still keep a lot of information, but also smooth the curve out. So let's here's a partial autocorrelation graph. Here, let's actually use ARIMA. So usually when you see ARIMA, like the function, if you program it like in Python and whatever, it's going to be a ARIMA function, and then it's going to ask you for P, D, and Q. So it takes 3 values. It wants the partial autocorrelation, the trend integration, and the moving average. And we went over how to get all those. So we have our full function here, and then we can get our partial autocorrelation. It looks like we have a partial autocorrelation. I'll try saying that fast, of 1. So we see 1 significant lag. So that means if you take lag 1, you can basically use it to regress on your function, or only the point after it is predictive of the next point. We have a first difference of 1, where if we take the first difference of this, we see the trend go away. So we have a trend integration of 1. And then for our autocorrelation, again, skip 0 because we don't care if it correlates with itself. We have 1, 2, 3, debatably 4 points. It's kind of on the edge of that confidence interval for autocorrelation. So you can decide to put in, decide to not. So here, if we fit an ARIMA of 113 onto it, we get something like this, which it's a little bit, lag. So maybe this is actually ARIMA 114, but you can play around with it and see, what fits the best. And this is all without, this is no machine learning, no deep learning. This is literally just using the behavior of your time series to fit to it, which is pretty neat because before they had the computational power to, do all this fancy machine learning, they were doing stuff like this. And it's still used very much because this is very explainable. Like I can tell you how I got this model. Like, well, I looked at, the partial autocorrelation, I looked at the trend difference, and I looked at the moving average, and I basically made a model off of that, and here's what I got. So now we want to check our model's performance. And we've all seen like residuals where you fit some line and you take how off that line is from your, real data. So here it's like we fit a linear line, and here's the actual data, and we have these residuals, which is basically the distance between your line and what's actually true. And you can sum up all of these residuals and get an MSE, but this is not sufficient. Like it's a good, metric to kind of see how well we did, but it doesn't tell you the full story. It's just a single number. So what else can we do? So in time series analysis, to really determine like the validity of your model, you need to do residual analysis, which means you not only need to look at your MSE, you need to look at how your residuals behave. So if you've seen this notation, it's common in papers like either IID or IIND. It's independent, identically, normally distributed. And that means, in less words, if you plot your residuals and if you make a histogram of your residuals, they should all be independent, right? So they should have nothing to do with each other. They should have no correlation. They should be identically normally distributed. So they should all come out of the same normal distribution or same. There's other like IID designations, like you can have like random distribution, but they should all come out of the same distribution and they should all have independence from each other. And you know that you have a good model if your residuals are IIND, because that means you're not missing any behavior in your time series. Because if you find, like next slide, if you find a pattern in your data, so these are randomly distributed. So we say this is like white noise. Basically, you fit your model the best you could to your line, and the rest of it is noise that cannot be fit. And that just has to do with your data and, you know, the sampling technique. But if you see any patterns within your residuals, that means there's latent behavior in the line that you didn't capture, because your residuals, these have like correlation to them. So this could be, there's like a curve in the data and you fit it too straight, so you missed a curve. So all your residuals are going to show a pattern that show how you missed that curve. And this is not good. This means your model is insufficient because there's behavior you're not accounting for, you know, in your data. So yeah, so how do we look at this? A very powerful tool to check for like residual behavior is actually our autocorrelation function, as you recall, because it tells us how well our points correlate to each other. So if you have your, you know, your time series, we have a fit to it. We got our residuals look pretty, you know, independent and normally distributed, I guess. But how do we really check? You need to look at your autocorrelation. And as you can see here, again, we don't care about zero, but everything is below our significance level. So there's no significant correlation within our residuals, which means we're sure they're actually independent. There's no behavior in here that we're missing, that our model is missing. There's a couple statistics that actually quantify this. There's like Durbin-Watson statistic, which kind of is a summary of your autocorrelation. It's a really weird statistic. It goes between 0 and 2, where 2 is the best. I don't know why they normalize it that way. But depending on what kind of residuals you're looking at, there's different types of statistics that say, hey, there's, you know, your residuals are all independent and normally distributed, your model's good. So now we need to talk about forecasting, because why did we do all this work to fit our data? This was also fit with an ARIMA model, actually. So we kind of saw like a rough shot one, but in this case, ARIMA worked really well, and you can barely tell the data is there because the fit is so close to it. So when we're doing forecasting, we basically want to continue our regression from, you know, we have known data, we fit that, now let's extend it into time periods that we don't know about it. And a really good test of how well, you know, you fit your data is to do like a train test split and have your forecast. This is our forecast is forecasting on the testing data, and then we can compare the error of the forecast to our testing data. So you might be wondering, why does our forecast look like a sideways umbrella? Well, when we're predicting the future, we really need to be like honest about it, because we actually don't know, and we don't have complete certainty. We can have some certainty, but it is the future. So what this green line is, the actual forecast is the average or like mean value we anticipate getting. But obviously the line is going to dance around. And then this, you know, cone shape around it is a confidence interval. So basically saying plus minus around the mean, what could happen. So like a real forecast or real prediction will always have a confidence interval around it. If it doesn't, that means they're lying to you, because they're saying that they have absolute certainty that they have the values. But being data scientists, especially if you're reporting to investors or something, you probably don't want to do that. So we're going to say, okay, we expect these values, like on average, it should be this value, but also it could be in this range. And the canonical shape basically comes from, as we go further into the future, the less certain we are of our forecast. So like, you know, T plus 1 outside of our known data, we can be pretty sure what that's going to be. That's not too far out of our known model, but as we go out farther, it's going to be more and more uncertain. So now it's time for a demo. Zoom, I don't want you. Okay. No. Yes. Yeah, we can do questions.
I was just wondering, like in the regular regression, we talk about overfitting. Here in the history, ARIMA is almost matching the.
Yeah.
Maybe wrong, but what is the? How do you look at overfitting in a time series? Does that even exist, or how do you?
Yeah, that's a good question. It depends on your problem, but I mean, you can address overfitting how we kind of traditionally, you know, determine it in like our machine learning perspective, where we have our forecast on our training data and we see how well that forecast actually lines up. But you also need to take into account the confidence interval, because if you're not exact on your testing data, but it is within your confidence, you are kind of covering it, or you're at least admitting that data is possible within your forecast. So it's a little bit different question, especially when we look at regression. Again, in a machine learning perspective, we're trying to get it exact, like here's our prediction, how well did it do in predicting this line. But in time series, when you're forecasting, that confidence interval kind of makes it a different game, because you say, here's what we expect, but here's also what can happen. So overfitting becomes more of a question of like, how much of a confidence interval spread can you accept? Like if you're saying like, I can say it's this value plus or minus 1%. If you're in certain cases, that would be fine. In other cases, that might not be. Like let's say, if you're just, I don't know, what's an acceptable one? Like if I say, I know the temperature tomorrow plus or minus 1 degree, that's probably fine. Like people are going to accept that as my confidence. But if I'm like building an aircraft and I'm like, I machine this part like plus or minus, 1 centimeter, that could be catastrophic. So the confidence you want really depends on your situation. Yeah, so let's actually put everything we talked about into practice as we do. So first, I'm importing a bunch of models, as that's how Python works. You just import libraries and use them. And a lot of this is stats models. This is a very interesting and very thorough library of different stats models. It has your exponential smoothing, as your ARIMA. I think you even can do like all your linear regression, and everything we covered can be covered in the stats model library. And so obviously the main time series everyone thinks about is the stock market, because we all want to get rich. So let's predict the stock market and make some millions. So let's take 2 stocks, or a stock and the market, because some people say just invest in the market, take your time. And then some people are like, no, like buy the best performing stocks so you can beat the market. So we're going to take Apple, AAPL, and we're going to take SPY, which is the index for S&P 500, which is a representative of the market because it's the 500 largest businesses or companies. And we're going to take that data from, it looks like 2017 to 2022, because that's when I did my project on this. So let's say 5 years of past data. Now we can look at, the Apple, or not Amazon. I messed up. This was what I did for the project, but I decided to, switch it to just the market for purposes of this tutorial. So now we're going to compare, Apple to the market. And so this data is pre-processed to us, where at the start date, it's 0, because I'm looking at percentage growth from a certain date. So, you start, and on that day it has 0% growth, because that's the starting. And as it goes up, that's kind of the percentage growth from the starting date we picked. So like here, they kind of look the same, but we can see
from the previous day.
It is from the first date. So from 2000, whatever date, 2017 to whatever date you pick, how much did that grow? So like we can see Apple from, the first day we picked to 5 years after grew about 300%, and the market grew about 55%-ish. And this is cool because we get to see like COVID effects and recovery. So this is like some atypical market data. So now we want to model these. So we want to regress to them and then make a forecasting model. So then, we can know what the market's going to do, and we all make millions of dollars. So these are pretty, cyclic, right? We're using our terminology. These are cyclic trending time series, and they're pretty jagged and chaotic. So I think we need pretty sophisticated models to actually determine what's going on here. Because I think a simple polynomial or line fit won't do. Dummy variables is not seasonal, so we can't use that. So I went with exponential smoothing and ARIMA, because those are some models that can fit pretty chaotic behavior. So first, we're going to do some exponential smoothing on our time series. And first, we do a classic test train split, because I want to make sure I can forecast on it and like get our actual model performance. And it's really just, if you use sklearn, the stats model library works is pretty much the same, where I just call the exponential smoothing function on our training data and say, hey, fit this. And then for forecasting, you say get forecast, and then you tell it for how many time periods do you want to forecast for. And it's a nice little summary frame that will tell you what the forecast is or the mean forecast. It won't tell you like an exact forecast because you don't have it, but it also give you a confidence interval. I'm also keeping track of our residuals because I want to know like what is the error in our forecast. And then I can plot this out and we get our nice regression fit to this Apple stock. And we also get a forecast, which is doing pretty well. It's like the mean like makes sense where it's at. And also the confidence interval just about covers all of our testing data. So it looks like it's saying, okay, within confidence, this model could kind of say that you can get these values. Again, if let's say you own a hedge fund and or not you own, let's say you work at a hedge fund and your boss is like asking you what stock should we invest in? And you're like, well, Apple's doing well, and I can tell you by, I think I projected in the next 100 days, Apple could be down here or it could be up here. Is that an acceptable, range for us? Do we want to take that risk? Same thing for the market. We're giving the kind of mean expected value we would think would happen in our forecasting time range, as well as giving a confidence interval. Now,
so while predicting the exponential times, how many points did you take before?
All of them. That's what exponential smoothing is. It's so like for the T+1, like first forecast, it's taking every single point before it. And then you use a weighting scheme to add a discount factor or like a weighting factor to each of these points before it.
What 1,000 days?
Yeah. So by the time you get to the 1,000th point, by the time you get to that, like, 1,000th point, like once you get to like, if you start at T0, the discount factor on this, it might as well be 0, right? Or probably these, yeah. So realistically, it's probably using the past 100 points before the discount factor gets out of hand and takes everything out. Yeah, so this is the summary table you get from using these models. So it'll give you a mean because you're forecasting. It can't give you an exact value because it's kind of dishonest to say like, I actually know the future. It's saying, here's what we would expect in the future, and here's how confident we are about it. And then we can go to ARIMA. So I made a little handy dandy helper function that just calls, the partial autocorrelation functions we need. And I did that on Apple and SPY. And we can see here kind of the 3 components you need to build an ARIMA model. And partial autocorrelation is pretty easy. It's 1, so that means that only the point before the point you have is kind of regressive to it. But most of the point, like all the points covered in this autocorrelation plot show that they're all correlated. So they're heavily correlated, but they're not very regressive, which is kind of weird to think about, but there's like mathematical justification for it. If you look into the actual definition of partial autocorrelation, it's like the correlation between points with like insignificant points like factored out of it or something. But what we do in this case, when it looks like you have all these like points that are correlating, is we usually cap it at like the 5 or 10th lag, because once you get past so many points you're taking into consideration with your correlation, they stop having like a big effect. And then
like you are the model, you are taking all the points. That's why it's like every point, every possible gap has a correlation.
Yeah, well, this is saying that if you take any point, the last 20 points before it are correlated to it.
We're taking that, like we're taking all those points to make the prediction from the T+1.
Yeah. Well, this is ARIMA. This is an exponential smoothing. So the autocorrelation just tells you, given any point in your time series, the past at least 20 points are correlate with that point. Yeah, that is weird, especially when you look at what our data looks like. And then in both cases, the first difference is sufficient. We take the first difference of both series and we see the mean or the trend in our data cancels itself out. So we can say that this is a ARIMA of 1, let's see, skip this, 1 and then 5. Let's just cap it at 5, right? which is we're lucky we can use the same ARIMA model on both of our time series because they kind of behave similarly. And then we do the same thing. We do a little train test split. We fit a little ARIMA model to it. Yeah, I did ARIMA order. So you give the parameters of your PDQ as 115, and then you fit that. And here we get a nice ARIMA model plus, again, a forecast, just like those exponential smoothing models. So now how are we gonna turn this into like cash for us, right? we gotta analyze our model. So here, look, I took all of the mean squared errors. Like it looks like ARIMA beat it out. So we're gonna use these models to get rich, right? Yeah. Or are we missing something? What is something we're not doing? Exactly. We sell, oh, MSE small, good. No, bad. Like when you're actually fitting a model, you need to look at how your residuals behave. Like what are you missing so you can, make a more honest report. So if you say, oh, look, MSE small, and then that's like your first level of analysis, but then you actually need to go into it. So now I put this here intentionally because I don't want to see you didn't want to do it, but ooh. Are those IIND, what do you say? Do those look independently, identically, normally distributed? No, and we can kind of tell that because of how we forecasted, right? Because we're forecasting this mean line and there's still behavior going on, so we're obviously going to miss it. But that doesn't mean that our model's junk, right? Because we're still being honest about, hey, we're trying to predict the future. We don't actually know it, so we're going to give you this confidence interval. And this kind of goes into a discussion of like, how do you trust your model? Like, how do you, like, if you're trying to predict the future and the computer gives you an answer, what gives you confidence in that answer? And that's a really open discussion, right? Because we say that all models are wrong, but some models are useful. So how do we choose if the model is useful or not? Like if I were to give you this and say, hey, are you going to invest in, Apple or SPY? Would you take this information? Like what's convincing to you, I guess? Just food for thought. The source. The source, yeah. What? Yeah, so these confidence intervals, the way they're calculated is they actually take into account the variance of the data you fit before. So as we see, there's highly variable data because it's the stock market. There's a lot that goes into how the stock market behaves. It's honestly mostly sociology and psychology. Not some people pretend that there's actually business math that goes into it. I'm not going to comment on that, but we can see that this is very highly variable data beforehand. So if you're saying, okay, I'm taking this highly variable data, I'm trying to predict what it does in the future, you can't really be that confident on what it's going to do next, right? Or you couldn't honestly say, I know exactly what the stock market's going to do. Like it's definitely going up this percentage point. No, you're saying it was trending upwards in general, but it's very chaotic in the short term. So when you're saying, especially only it's going, let's say upward trending in a 400-day-ish span. If I say, okay, what's it going to do in the next like 100 days? You're like, well, it should kind of go upwards, but I also don't really know. So, it's a lot of like, here's our confidence. It's very chaotic. So it should land within here. And if you take the last point and the first point of this, it does slightly tend upwards. So I think I checked that. Yeah. So it's like, okay, it should be slightly tending upwards, but in the interim of it kind of trending upwards, it's going to do anything. But if you do fit these models and find confidence bounds for other more predictable time series, you'll see much tighter confidence intervals. Which like if you have very regular data, your confidence interval is going to be a very tight cone, and you can say, oh, we're pretty good at like, figuring this out. Just a cool kind of after thing to show you that these models have is they have a simulate function, which is basically based off of our fit and our prediction. Can you kind of Monte Carlo us a kind of guess at what the data is going to look like? And it can get pretty close. And you can do repetition. So basically run like 100 simulations or like 100 different random rolls of how this could land. And what's interesting, if you do this and you run it, run 100, yeah. So there's this big spread. And what we just did is we recreated our confidence interval, right? Because we said we're confident in our values in this spread, okay, we did 100 simulations of what could happen, and they all just like make our confidence interval again, because that's what we're like, confident in saying what could happen in the future. And yeah, so that's oh yeah, see, there's a lot of forecasts. Wow. So yeah, that's time series analysis. There's a class about it. It's like stats 773. The professor's good, but he's a really, really hard grader. So just keep that in mind. I kind of took that entire class and condensed it down into like all the models we use. There's a couple models I had to leave out. Like there's something called SARIMA, which is seasonal ARIMA, which is the same ARIMA model, but then you have a different set of like a different PDQ for the seasonal components. So you basically do seasonal decomposition and do ARIMA for the trend, and then do ARIMA for the seasonal, and then put it together. But yeah, do we have any questions on time series analysis? Yes.
So the forecasts, like some of the forecasts go outside of.
Yep.
What's the reason why that?
Well, so like you're saying these like these like this simulation.
No, like the one that you were showing.
Like this, like it. So this blue part is actually our testing data.
Oh,
And the testing data going outside of our confidence interval is actually a threat to validity of our model, because that means that the data could go outside of our confidence in the future, and we didn't account for that. So either make your confidence interval bigger and actually be more honest about it and say, okay, values could land out of this, but now we're less certain. And at some point, your confidence interval, like I would argue, these confidence intervals are so big that it makes your model kind of meaningless, because you're saying we're confident that the stock market will grow this much in 100 days plus or minus like 100%, right? Because it's like centered around 3 or plus or minus 50%. But that kind of makes sense, because the stock market, like a lot of things can happen in 100 days. Like we know, like especially if you look at COVID, totally tank the stock market. There's no way to predict that. So yeah, I would say, I mean, it's probably as good as this model is going to get. And if anyone actually could model the stock market, they'd be very rich, and no one really has. So any more questions?
Predicting this January, should we reduce ARIMA?
So SARIMA is meant for seasonal data, and this is a cyclic trend, right? Because it doesn't have regular patternicity. So SARIMA wouldn't be appropriate for this. But for cyclic, like highly cyclic trends, which cyclic basically just means there's like random noise in it. These exponential smoothing and ARIMA models work really well, because they are accounting for every point and how it relates to the next point. Like
Generally, because you need all the points.
yeah, or at least local points. Because remember, we looked at how much moving average we should have. Like ARIMA, like let me go back to the slides real quick. Let's go to when I described ARIMA. Because what ARIMA is doing is it's taking into account, these three factors: the partial autocorrelation, the trend integration, and the moving average. And it's basically just putting all those in an equation with the data it's seeing to fit your model. So this isn't like ARIMA is not exponential smoothing. It's not looking at every point, but it's looking, I believe it looks at the moving average window, and then it looks at, we have a partial autocorrelation of 1. So it's going to look at the next point, and also it's going to take the trend into account. So it's kind of like taking your local window and trying to, predict what's coming next. And I think this is yeah.
So how is the model? We have to provide the parameters every time. We have to interpret from the plot.
Yes, yeah. I mean, there's definitely automatic software that can find PD and Q for you, which it'll just do this for you. It'll find the partial autocorrelation, find the significant lags, find the degree difference, and find the autocorrelation. I just did this by hand, but there is like whatever stats programming can use, just like ARIMA, like find parameters, and it just runs a optimization algorithm to figure out the best. Yeah.
And
But
for time series data, always we have to take the latest data as tested, or we can take from the beginning to the
like
so
to,
like the training test device is also so, like we are always taking the tail of the thing.
yeah, because we're forecasting, right? So
Yeah.
we want to know how future proof our model is. So generally, at least I've always seen you take
Yeah,
your
that's-
like
that's what I
last,
think, but
yeah. But you could, I mean, you could take, I guess, any chunk of data as long as it needs to be sequential though. You can't take random data because you're now like, yeah, that's because now that doesn't make a time series anymore. You've broken the sequentialness. Yeah.
Sounds good.
I don't want doubt like because it's GPT question and it has trended. Can do a mean or median and
Yeah, like
Actually, I
how,
worked on that problem like so online. So the project I worked on is like we are measuring pollution data. So like at every second, the sensor will measure how much PM PM 2.5 is present in the in the air. So what we would do the exponential smoothing. Like say you have got 10 seconds data, then 11 and 12 data are missing, and then again you have got 13 to 20. So what we would do an exponential smoothing in both directions to get
yeah.
the data.
Yeah, and there's also like different arguments for using different moving averages, right? Because some moving averages, like it takes your first point and then you take the 10 points after it, say. Some of them, they take the 10th point and take the 10 before it. Some of them, it uses that point as the middle value and takes 5 on both sides. And there's different smoothing values to and how you can like interpolate your data. And it's just kind of, yeah.
That is a huge problem in this, so that's the research data, data engineering.
Yeah, like how do you, yeah, that's an, obviously for us data scientists, a very active area of research. If you have missing data, how do you fill it in? Like, and how do you fill that in a statistically valid way, right? Because you can't just like put any value you want. It's like, well, does the average work here? Sometimes the average doesn't make sense for your data. Like if you're looking at, let's see, like the height of like your population, in correlation with the like weight. If you're using averages, you're throwing your data way off. So yeah. Okay. Thanks everyone for coming, and thanks for surviving your midterms if you had them, and have a very good spring break.